Hey folks, today's topic is factoring. So your goal, our learning target, is to be able to look at a polynomial and be able to break it into its prime factors. And you'll know you'll be successful at this when you can just look at a polynomial and decide which factoring method to use. So we're going to have 4 different factoring methods. And yeah, so let's get into it. So let's just talk a little bit first. What is factoring? So maybe you don't even know what that word means. What is factoring? Well, factoring is the mathematical operation where you break down, or process maybe is better than operation, process where you try to take something and you try to break it into its prime components. Now, we've done this with numbers before. We can factor numbers. That's kind of an elementary school topic. But that can give us the idea of what factoring looks like. So I take the number 24, let's say. I'm going to find the easiest factor that I can. So I'm going to break this down into 2 and 12. I could keep going because I haven't broken this into its prime factors, because 12, while 2 is prime, 12 is not. So I can break this down again. So I've got my 2 times. Now I'm going to break down the 12. The 12 is going to break into 2 times 6. And I notice again, I have a factor that can be, a term that can be factored even further. So I'm going to break that down again. 2 is prime. 2 is prime. I can't factor them anymore. 6 is factorable into 2 times 3. And now I have all what we call the prime factorization of 24. This is the only way you can, no matter if you pick, let's say you did 3 and 4 first. What's interesting is everybody will end up, no matter how you decide to break down a number, you'll always end up with the same prime factorization at the end. And that's what's interesting about factoring. So it doesn't really matter. As soon as you can find a factor, you're good to go. This is called, I'll write a little note there. This is called the prime factorization. That means we factor it as far as we possibly can. We break it down as far as we possibly can. All right, so our first move is called factor out. And you want to do factor out. Sometimes I think Wojo calls this GCF factoring. But here's my big thing that I want to point out. You must always try this first. So when I look at anything that I'm going to try to factor, I always try to take out a common factor first. So a greatest common factor. I try to factor something out. And what I mean by that is if you're looking at these two terms, is there anything that belongs to both of those terms? And we clearly see that. Then let's look at these are called coefficients, by the way. That's called the base. The variable in this case is the x is called the base. And then the 6 is called the exponent. So we want to make sure that we use those. Actually, let's go ahead and put that on the side over here. A times x to the n. This is called the coefficient. I wish I would have put it over here. I'm going to move it. I don't like it over there. I don't have enough room to write everything. So I'm going to write it over here. A times x to the n. This is called the coefficient. This is called the base. This is called the exponent. So I'm going to use the proper terms. If this was Algebra 1, I might talk about the number out in front, or I might talk about the little number up at the top, or I might say power, actually. But I want to try to get in an advanced class like this. I want to make sure that we talk about these things in their proper, with their proper names. So as I look at the coefficient and I look at these are called terms too, by the way. This is called a term, that's called a term. As I look at the first term and I look at the second term, I notice they both have a 7. So I'm going to factor out a 7. Then I look at my bases and I notice that I have an x to the 6th and I have an x to the 2nd. So in common, they have at least 2 x's, so I can factor out 2 x's. Now this is the kind of tricky part, if there is a tricky part to this. You have to build back in here what you had up here. So in other words, if I were to distribute this, I need to get back to having 7x to the 6th minus 35x squared. So 7x to the 2nd times what would make 7x to the 6th? Well, 7 makes the 7, so that's easy. X to the 2nd, I need 4 more x's to make x to the 6th. And then I need to, here I am again, 7 times what would make negative 35? That would be a minus 5. How many x's do I need? Well, I've already got 2, and I need 2, so that's good to go. Now, I wouldn't box this in if I could factor this some more, but in this case, we can't factor this. There is a little bit of factoring that could go on there, but I'm not going to worry about that part. Or you're not going to want to break it down more than that. At least not yet. Maybe when we get into, I think it's unit 2, we'll talk more about that. All right, so here we go. I'm going to do another one with you, and then the last 2 you're going to try on your own. So 12 and 28, do they have anything in common? Yeah, they have 2 in common, right? But you always want to try to find the G in GCF is the greatest common factor. Is there a number bigger than 2? So yeah, so you have to think a little bit harder. And if you're somebody who struggles with finding common factors, then you got to go through the sort of hassle of breaking down these 2 numbers and seeing what's the biggest number that goes into both of them. 1 and 12, 2 and 6, 3 and 4, 1 and 28, 2 and 14, 4 and 7. So what's the largest number that goes into both of these? 4. Now I kind of always describe it as, in my mathematical experience, when I was in 4th or 5th grade, whatever, I learned my multiplication tables, and then I learned them again when I started to do factoring, because you have to apply all those multiplication facts. And some of you guys can just look at that and boom, you got it. That's awesome. Some of us takes a little bit longer, and I definitely was in that group when I was younger. So, okay, so our common factor is 4. So I'm going to take out a 4. How many x's? They have 3 x's in common. Okay, now I got to build back what I had before. 4 times what makes 12? 3. And I need 2 more x's. 4 times what makes 28? 7. And I need 3, but I've already got 3, so I'm good to go. All right, I'm going to encourage you to pause here and try to do the next 2 on your own. All right, let's see how you did. So, look, 5 and 6, they only have, everything has something in common. What number goes into everything? 1. If it makes you feel all warm and fuzzy inside, put the 1 out there. I'm not going to do that because I know that if I don't write anything, that implies a 1. So x to the 5th and x to the 2nd, that has an x to the 2nd in common. There's the 1 that I'm not going to write. Now I got to build back. I have the 1, I need 5 to get to 5. I have 2, I need 3 more. I have 1, I need 6. I have 2, I need 2. Done. And then finally, 4 and 28. Well, we just broke those down. So 4 is the largest number, and 4 goes into 28. So we can take that out. They have, they don't have any common variables. That's okay. X and Y have nothing in common. So the only I can take out the 4. So what do I need to build back? I just need the 4 x's, and then I need 7 y cubes. All right, next topic is called difference of perfect squares. I call these dopes. Miss Musial calls them special doubles. So depending on how you want to think about them, it's up to you. I just need you to be able to recognize them. Let's do this first. Let's list the first. Let's list the first 20 perfect squares. See if you can list all 20 of them. All right, let's see how you did. So the first 20 perfect squares. So 1 is the first perfect square because 1 times 1 is 1. 4 is the next perfect square because 2 times 2 is 4. You see what I mean? The third one will be 3 times 3, which is 9. Fourth will be 16, 4 times 4, then 25, 36, 49, 64, 81, 100. Then 11 squared is 121, 12 squared is 144. I would expect everybody in pre-calc to get at least that far. The next row gets a little bit trickier, but just to point out, a perfect square is any number that you want. When you square it, that's that perfect square in the list. So if I wanted the 7th perfect square, I would take 7 and square it. 1, 2, 3, 4, 5, 6, 7. 7 squared is 49. All right, so let's see if anybody got the next ones. Would be 13 squared, which would be 169. 14 squared is 196. That's how I learned those two. It's because they're flip-flops of each other, kind of. That was 13, 14. 15 squared is 225. 16 squared is 256. 17 squared is 289. 18 squared is kind of a weird one, 324. Then 361. Then 400. Now I put dot there because that list could go on and on and on as long as you wanted. All right, so let's try it. Dope's difference of perfect squares. So look at what happens here. I've got to find two numbers that multiply to make x squared, and then I've got to find two numbers that multiply to make 4. But when I distribute them and I add them up in the middle, they've got to cancel out because there's only an x squared. There isn't a plain old x term. Now, first of all, could I do a factor out? Is there anything in common here? No. So I checked that first. Then I noticed that x is a perfect square, and x squared is a perfect square, and 16 is a perfect square. So this factors into x plus 4 and x minus 4. Now these have another special name that's going to become important later on. These are also called conjugates. Look at what happens when you distribute conjugates. So what's x times x? That gives me the x squared. And then I go x times negative 4. That's negative 4x. 4 times x is positive 4x. So those two terms add up to 0 in the middle. And then 4 times negative 4 is 16. That's why you can't use like 8 and 2. 8 and 2 makes 16. 16 and 1, those make 16. But those are not going to add up to the 0 in the middle when you distribute. When you have coefficients, that doesn't change much. You just have to account for those coefficients when you distribute. So now instead of having x times x makes x squared, I need 5x to make 25. And then I need to make 6 would be plus 6. And then 5x minus 6. All right, you try the next one. See how you do. Or I pause and try both of them. There's some weirdness that'll happen, so don't freak out if you're having a hard time. All right, so the weirdness that happened here is that I don't know if you looked and tried to factor out. When you looked at this at first, you saw 6 and 54 and said, hey, those aren't perfect squares. Now, you can actually do this. We're going to do this in later on, I think second semester. No, maybe first. I can't remember exactly when. No, it's definitely first semester. I think it's unit 2. We're going to factor this, and it's going to break into root 6 and root 54. But what should you try first? You should try to always factor out. And at the very least, 6 and 54 has a 2 in common. Is there anything bigger? Well, yeah, 6 goes into both of them. So I'm going to take out a 6. Notice x and y aren't in common, so that's going to be a 6x squared minus a 9y squared. Now all of a sudden we do have dopes. We have a difference. This is a perfect square. 9 is a perfect square, and y squared is a perfect square. That 6 still needs to count out front, but then from there, I can do dopes to factor that next part. And then 100x squared plus 81. Hopefully that jumped out to you. Rightfully so. We cannot factor this. this would be the best we can do. Cannot factor. And I'm going to put in parentheses over real numbers. Over the real numbers. You can factor this, and we're going to do that again in chapter 2, unit 2. You can factor this over the imaginaries. Remember those little eyes? This is not going to work because, like we said, this is called dopes, difference of perfect squares. This is a sum of perfect squares. SOAPs. We can't factor SOAPs over the real numbers. All right, so just kind of let me kind of break things down so far. Always to look for something to factor out first, no matter how many terms there are. I made this simple where they always had 2 terms, but you could factor out with 3 or 4 or 5 terms. Whenever you see only 2 terms, that's a good thing to that's a good way to think of dopes. When you see only 2 terms, try to do dopes. That's kind of a giveaway there. Now, if they're not squared, if this was x squared minus 16x, that would be a factor out. That wouldn't be dopes. But just to point out, when dopes only works when there's only 2 terms. You can't do, there's not dopes with 3 terms. And then factor by parts has its own giveaway. As soon as I see that I have something that has 4 terms, factor by parts for sure. This is something, anytime you see 4 terms, the only way you're going to be able to factor it, besides maybe doing a factor out, is by factor by parts. So factor by parts is kind of interesting. You want to look at the first 2. First of all, is there anything I can take out? 2, 2, 2, but I can't take a 2 out of that. I can take a 5 out of those, but not out of those. So no, not everything has an X, so I can't factor out. So I want to think about factor by parts. I want to think about this as 2 separate pieces. Notice how I'm underlining those 2 sections. And then I left a space here. That was purposeful, because I want to take that sign out. That's a reminder that whatever this sign is, I've got to factor out that sign. Okay, so I'm looking at 30x cubed and 12x squared. This is a factor out. 30 and 12, the greatest common factor is 6, and then they have 2 x's. Now I need to build back what I had before. So 6 times 5, and I need another x. 6 times negative 2, and I don't need any more x's. This is what I'm talking about here. That middle sign has to come out, whatever that sign is. That's an automatic. That's pretty much the only trick that you've got to remember that's sneaky about factor by parts. All right, then I look at 25 and I look at 10. They both have a 5. Now look, what are you really factoring out here? You're factoring out a negative 5. So that leaves behind a positive 5x, and this was a positive 10, so I need to have a negative 5 and a negative 2 to make back my positive 10. Look, distribute this again, and you should get exactly what you had before. Now, you know you did factor by parts correctly if the 2 parts have something in common. So they both have this 5x minus 2. I'm going to factor that out of both of them. And then that leaves behind 6x squared, subtract 5. I mean, that's exactly what we did up here. Well, actually, we don't even have to go that far. We can just look at these 2. You see how these both had a 6 and an x squared in common? So they both had a 6 and x squared, so I factored those out once. Because when I distribute, it turns back into 2 of them. So a lot of kids look at this and say, why is there 2 of them here and only 1 of them here? That's because we factored them out. And so if I asked you to distribute, you would take this chunk and you'd give it to that term. Then you would also take this chunk and give it to that term. So you do still have 2 of these. It just doesn't look like it. Doesn't look like it. All right, you try the next one. All right, let's see how you did. So this is, I've noticed that there are 4 terms. So I'm going to leave this. I'm going to draw a little arrow to indicate that that has to come out. 15 and 21 share a 3, I think. Yep. And 2 x's. That leaves behind, I need a 5x and I need a 7. I'm taking out a positive this time. 5 and 7 only have a 1 in common. Now, up here, I didn't write the 1 because I knew the game was over once I factored out once. It was this. It might be a good idea to write the 1 here because when you factor this piece out, you've got to remember that you still have to account that this was a term. So that leaves behind 5x plus 7. My math voice is happy because those two are common. So now I can take that out first. And then that leaves behind 3x squared. Now this is where kids make a mistake too. That's what I'm saying about this 1. If you didn't write the 1 here, when you factor this out, it feels like there's nothing there. But you have to distribute this back and get what you had the line before. So I need to have a 1 as kind of a placeholder so that when I distribute the 5x plus 7, it gets multiplied by that 1, and so I still have 2 of them. Last one, at least on the front. Give it a whirl. All right, so I'm going to highlight. I like to draw that little arrow. You don't have to do any of that if you could just see it. Boy, it helps me. So these two don't have a coefficient in common, but they do have an x squared in common. That leaves behind 8x subtract 7. I'm taking out the minus. 72 and 63 share a 9. That leaves behind 8x. Remember, I took out a negative 9, so that's going to make this a negative 7. Subtract 7, which is good because I want those groups to be the same. So I take out the common factor. My other quantity becomes what's left over, and I don't box this in yet. Hopefully you didn't fall for it, but you've got it. That's what this game is. That's what today's topic is, being able to recognize these moves. Do you see the move now that I've pointed it out? My math voice is screaming when it sees this. It's like blinking on the page. So I can break that down again because that's dopes. That breaks into x plus 3 and x minus 3.